In this video, we are going to discuss the types of molecular velocities and Maxwell Boltzmann distribution of various velocities. It is very important to note that gas molecules randomly move in all the directions, and during these motions they collide with each other, as well as they collide with or collide against the wall of container. And during these collisions there is an exchange of energy which changes the speed or velocity as well as kinetic energy of these molecules, and therefore there is a broad distribution of various velocities or different fractions of molecules. So in gas sample, when gas is confined in cylinder, gas molecules have different velocities like most probable velocity, average velocity, root mean square velocity, etc. These are the various types of velocities. So first of all, we are going to discuss the types of molecular velocities, which types of velocities are possible. The first important type is most probable velocity of gas molecules. And what is the meaning of this? The velocity possessed by largest fraction of molecules in a gas is called most probable velocity. Actually, this most probable velocity, it is possessed by largest fraction of molecules in a gas sample, and this most probable velocity, it is given by, or it is equal to under root 2 RT upon m, where R is a gas, universal gas constant, T is absolute temperature, and m is a molar mass of the molecule, gas molecule. Now from this relation it is clear that the most probable velocity, it is inversely proportional to molar mass and directly proportional to temperature, absolute temperature. So most probable velocity, it is inversely proportional to molar mass. Now consider the gas sample having two types of molecules with molar mass m1 and molar mass m2, and molar mass of one molecule, one type of molecule, it is less than the molar mass of other type of gas molecule. For example, m1, it is greater than m2, or m2 is less than m1. There are two different gases confined, or there are two different types of molecular weights possessed by a gas molecule. m2, it is less than m1. Okay, now the distribution of these two velocities or distribution curve according to Maxwell and Boltzmann, the distribution curve for these two types of gas samples, it is given by, suppose this is the distribution curve for one type of gas molecules with molar mass m1 which is greater than m2. So this larger molecules or molecules with larger molar mass, they move with little bit slow speed, and their most probable velocity, this is the most probable velocity of the gas sample 1. So this is the fraction of molecules possessing the most probable velocity. So this is UMP1, it is for the gas sample 1. Now consider the distribution curve for another gas with gas molecules of molar mass m2. As m2 is less than m1, these molecules of gas 2 move little faster than the gas molecules of gas 1. It implies that the most probable velocity for gas sample 2, it is greater than the most probable velocity for gas sample 1. And in short, we can say that the smaller molecules or molecules with less molar mass moves faster than the gas molecules with larger molar mass. So in this way, most probable velocity, it is inversely proportional to molar mass. As I said, as per this relation, most probable velocity, it is directly proportional to absolute temperature. It is directly proportional to absolute temperature. Again, consider the Maxwell Boltzmann distribution curve for a gas at different temperatures. Suppose same gas, it is considered at different temperature. So at little bit lower temperature, for example 100 Kelvin, this is the distribution curve for a gas, and here is the, so at peak position there is a most probable velocity. Okay, now suppose temperature is increased from 100 Kelvin to 300 Kelvin. So this is the distribution curve for a same gas at 300 Kelvin. So it shifts to the right side, and the distribution curve, it becomes broad. Now consider again little bit higher temperature at 600 Kelvin. Again the peak or most probable velocity, it shifts to the right side, and the distribution curve becomes broad, and this is at 1000 Kelvin. Peak is broad and most probable velocity, it shifts to the right side. Meaning of this is, lighter molecules, as I said, move faster than the heavier molecules. That is, it is inversely proportional to molar mass. But the most probable velocities, it is directly proportional to temperature. It means with increase in temperature, the most probable velocity also increases, and therefore the entire distribution curve shifts to the right side. And as temperature increases, the distribution curve becomes broader, and the height of peak also decreases. Meaning of this is, most probable velocity increases with increase in temperature. So most probable velocity at 100 Kelvin, it is less than most probable velocity at 300 Kelvin, which is less than most probable velocity at 600 Kelvin, and so on. So as temperature increases, most probable velocity also increases. So this is what is most probable velocity. Now next term is the average velocity or mean velocity, UAVE. Now definition of mean velocity or average velocity is arithmetic mean of various velocities of gas molecules. It is called as average velocity. Now consider n number of gas molecules having individual velocities v1, v2, v3, v4 and so on, that is up to vn. There are n number of gas molecules, and v1, v2, v3, vn, these are the individual velocities of these gas molecules. Now the average velocity, it is equal to v1, v2, v3, v1 plus v2 plus v3 plus v4 and so on up to vn upon n. So sum of individual velocities of all the gases upon total number of molecules, that gives the average velocity. So according to Maxwell, the average velocity UAVE, it is equal to under root 8 RT upon pi m. R is gas constant, T is absolute temperature, m is molar mass, and pi, it is also constant. So this is the formula for average velocity. Now next term is root mean square velocity, that is URMS. Definition of root mean square velocity is, it is the square root of average of squares of velocities of molecules of a gas. It is called as root mean square velocity. And root mean square velocity, it is given by formula under root v1 square plus v2 square plus v3 square plus v4 square and so on up to vn square. You know, v1, v2, v3, vn, these are the individual velocities, and n, it is the number of molecules present in a sample. So upon n. So this is the formula for URMS, that is root mean square velocity. According to Maxwell, root mean square velocity, it is equal to under root 3 RT upon m. T is absolute temperature and m is a molar mass, R is a gas constant. So this is the root mean square velocity. Now the relationship of these three velocities, or ratio of these three velocities, that is most probable velocity is to average velocity is to root mean square velocity, it is 1 is to 0.9211 is to 0.8165. Meaning of this is, largest fraction of molecules possess the velocity that is the most probable velocity. Okay, most probable velocity, it is possessed by largest fraction of the molecules of gas sample. Okay, so according to Maxwell and Boltzmann, the distribution curve, when we plot Maxwell speed distribution fraction versus molecular velocity, then this is the distribution curve. And you know, at the peak there is a most probable velocity. So this is the most probable velocity, its fraction is 1. So largest fraction of molecules possess this most probable velocity. Then this is the position of average velocity, and 0.9211 fraction, this is the fraction of the average velocity, it is less than most probable velocity. And this is the position of root mean square velocity, fraction is 0.8165. Ratio already I told you, 1 is to 0.9211 is to 0.8165. and this is the Maxwell distribution, Boltzmann distribution curve for the different velocities possessed by gas.